Somewhere near the center of a quiet suburban neighborhood of the Milky Way, a single ordinary star burns steadily against the blackness of space. It has been burning for nearly 5 billion years. It will continue burning for roughly 5 billion more. There is nothing particularly unusual about this star. It is not the largest, not the brightest, not the oldest. Among the hundreds of billions of stars scattered across our galaxy, it would be remarkably easy to overlook. And yet this star holds something extraordinary in its gravitational embrace. Stretching outward from its surface in every direction, an enormous region of space falls under its influence. Planets orbit within it. Moons circle those planets. Asteroids drift in ancient corridors. Comets fall inward from unimaginable distances, sweep close to the heat, then retreat again into the cold. And far beyond, the last known planet, beyond the icy remnants of the solar system's formation, a boundary exists where the wind from this star finally loses its strength, and the true emptiness of interstellar space begins. That boundary is where this journey ends, but it begins here, close to the light. The Sun is a sphere of hydrogen and helium, roughly 1.4 million kilometers across. If you could stand at a safe distance and watch it without any filter, you would see a surface churning with convective motion, bright granules of plasma rising, cooling, and sinking in a cycle that repeats endlessly. The temperature at the visible surface hovers around 500 degrees Celsius. Beneath that surface, conditions become progressively more extreme, until deep in the core, the temperature reaches approximately 15 million degrees. There, hydrogen nuclei are forced together with such pressure that they fuse into helium, releasing energy in quantities that are difficult to express in everyday terms. Every single second, the Sun converts roughly 600 million tons of hydrogen into helium. The small fraction of mass lost in that conversion becomes energy, and that energy slowly works its way outward through hundreds of thousands of kilometers of dense plasma until it finally escapes from the surface as light and heat. That light takes just over 8 minutes to reach Earth. It takes roughly 4 hours to reach Neptune, and it continues far beyond Neptune, growing weaker and more diffuse, but never quite vanishing. Not until something else finally overwhelms it. The Sun also produces something less visible, but equally important for our journey. A continuous stream of charged particles, mostly protons and electrons, flows outward from the solar corona at speeds ranging from 300 to 800 kilometers per second. This is the solar wind. It fills the space between the planets. It shapes the tails of comets. It interacts with planetary magnetic fields. And critically, it inflates an enormous bubble around the entire solar system, a region called the heliosphere, within which the Sun's influence dominates. The outer edge of that bubble, where the solar wind can no longer push against the pressure of interstellar space, is known as the heliopause. That is the true boundary we are traveling toward. But from here, standing close to the Sun, that boundary is unimaginably far away. The heliopause lies roughly 120 astronomical units from the Sun, and 1 astronomical unit, the average distance between the Earth and the Sun, spans about 150 million kilometers. The edge of the solar system, then, is approximately 18 billion kilometers away, and even that number understates the full picture. Beyond the heliopause, gravitationally bound objects may extend outward to distances of 100,000 astronomical units or more, a region so vast that light itself takes more than a year to cross it. This journey will carry us through all of it. We will pass through the realm of the rocky inner planets where worlds huddle close to the Sun, surface shaped by heat, volcanism, and impact. We will cross the asteroid belt, a broad corridor of ancient debris that marks the transition between the inner and outer solar system. We will visit the giant planets, worlds so large they dwarf everything else, with atmospheres deeper than entire terrestrial planets and moons that rival planets in complexity. Beyond the giants, we will drift through the Kuiper Belt, a vast ring of frozen objects left over from the earliest days of the solar system's history. We will travel through the scattered disk, where the gravitational influence of Neptune has flung icy bodies into strange, elongated orbits. We will approach the heliopause, where the Voyager spacecraft became humanity's first emissaries to interstellar space. And finally, we will venture into the theoretical vastness of the Oort cloud, a spherical shell of dormant comets so distant that the Sun, from there, would appear as little more than an unusually bright star. The distances ahead are real, the silence is real, and the journey, once it begins, moves in only one direction, outward into the deepening cold and the growing dark, until the solar system itself dissolves into something much larger and far more quiet. We begin by leaving the Sun behind and turning toward the first small world waiting in the light. The first world waiting in the sunlight is also the smallest. Mercury orbits the Sun at an average distance of roughly 58 million kilometers, completing one full orbit every 88 Earth days. It moves faster than any other planet in the solar system, tracing its path at nearly 48 kilometers per second. From a distance, it appears grey and scarred, a world that looks far more like our moon than like any of the other planets. And in many ways, that resemblance runs deeper than surface appearance alone. Mercury is a dense, battered sphere just 880 kilometers across. If you were to approach it from space, the first thing you would notice is the absence of anything soft. There is no atmosphere worth mentioning, no clouds, no haze, no color in the sky. A thin exosphere exists, composed of atoms blasted off the surface by solar wind and micrometeorite impacts, but it offers no protection and no weather. The surface is exposed directly to space, and it has been exposed for billions of years. What that surface records is violence. Mercury is covered with impact craters in every size, from small pits a few meters across to enormous basins hundreds of kilometers wide. The largest of these, the Caloris Basin, stretches roughly 1,550 kilometers in diameter. It was formed by a massive impact early in the solar system's history, an event so powerful that shockwaves traveled through the entire planet and created a region of chaotic, broken terrain on the opposite side of the globe. The Caloris Basin has been partially filled by ancient volcanic plains, smooth expanses of solidified lava that tell a story of a world that was once geologically active. Mercury's surface also bears long, winding cliffs called lobate scarps, some stretching hundreds of kilometers across the landscape. These are compression features formed as the planet's interior slowly cooled and contracted over billions of years, causing the crust to buckle and fold. Some of these scarps rise more than a kilometer above the surrounding terrain. They are among the most telling geological features in the solar system because they reveal something about what lies beneath. Mercury's iron core is enormous, relative to the planet's size, occupying roughly 85% of the planet's radius. No other rocky planet has a core-to-body ratio even close to this. Why Mercury's core is so disproportionately large remains an active area of research. One hypothesis suggests that a giant impact stripped away much of Mercury's original mantle early in its history. Another proposes that the intense heat of the young sun prevented lighter silicate materials from accumulating during the planet's formation. Neither explanation has been conclusively proven. Despite its closeness to the Sun, Mercury is not the hottest planet in the solar system. That distinction belongs to Venus. But Mercury does experience the most extreme temperature swings of any planet during its long, slow daytime, which lasts the equivalent of about 88 Earth days. Due to its unusual rotational relationship with its orbit, surface temperatures can reach approximately 430 degrees Celsius. During the equally long nighttime, Without an atmosphere to retain heat, temperatures plummet to roughly -180 degrees Celsius. That is a range of more than 600 degrees between day and night, a swing unmatched anywhere else in our planetary neighborhood. And yet, in the permanently shadowed craters near Mercury's poles, where sunlight has never reached, temperatures remain cold enough for water ice to persist. This was confirmed by radar observations from Earth and later supported by data from NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. The discovery of ice on the planet closest to the Sun is one of those results that initially seems impossible but makes perfect sense once you understand the geometry. Mercury's rotational axis is tilted less than 1 degree relative to its orbital plane, meaning the Sun never rises high above the horizon at the poles. Deep crater floors in those polar regions exist in permanent shadow, shielded from sunlight for billions of years, cold enough to trap and preserve volatile materials delivered by comets and asteroids. Messenger transformed our understanding of Mercury. Before its arrival, the planet had been visited only once by Mariner 10 in the mid-1970s, which imaged less than half the surface. Messenger mapped the entire globe, measured the planet's gravity field, confirmed the presence of polar ice deposits, detected unexpected amounts of sulfur and potassium on the surface, and revealed that Mercury's magnetic field, though weak, is genuinely generated by a dynamo in its liquid outer core. Mercury remains one of only 2 rocky planets in the inner solar system, with an active magnetic field, the other being Earth. We leave Mercury behind now, continuing outward. The Sun is still overwhelmingly bright. Space between the planets is empty and silent. The next world is closer to our own orbit, and in many ways, it is far stranger than the small grey planet we just passed. Venus orbits the Sun at an average distance of about 108 million kilometers. It is nearly the same size as Earth, with a diameter of approximately 12,104 kilometers compared to Earth's 12,742. Its mass is roughly 82% of Earth's. Its internal structure is believed to be broadly similar. An iron core, a silicate mantle, a rocky crust. In many respects, Venus and Earth began as siblings, formed from similar materials in a similar region of the young solar system. But something went profoundly wrong on Venus, or profoundly differently, depending on your perspective. Today, Venus is the hottest planet in the solar system, with a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead. That temperature barely varies between equator and poles, between day and night, between seasons. The entire planet is wrapped in a thick, crushing atmosphere, composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting at altitudes between roughly 45 and 70 kilometers above the surface. The atmospheric pressure at ground level is about 92 times that of Earth, equivalent to the pressure found nearly a kilometer beneath Earth's oceans. The reason Venus became so hot is a runaway greenhouse effect. Carbon dioxide is exceptionally efficient at trapping infrared radiation. On Earth, a relatively thin layer of greenhouse gases keeps the planet warm enough for liquid water. On Venus, an atmosphere roughly 90 times more massive, composed almost entirely of carbon dioxide, traps so much heat that the surface temperature stabilized at a point far beyond anything biology as we understand it could survive. Whether Venus ever had liquid water on its surface is one of the most important unanswered questions in planetary science. Some climate models suggest that Venus could have maintained temperate surface conditions with liquid water for billions of years before the greenhouse effect became irreversible. If true, Venus may have been habitable for longer than Mars ever was. The surface of Venus is hidden beneath those clouds. No telescope on Earth can see through them in visible light. Almost everything we know about the Venusian surface comes from radar, both from Earth-based radar and from spacecraft equipped with synthetic aperture radar systems. The Soviet Venera program successfully landed multiple spacecraft on the surface of Venus between 1970 and 1985, and several of those landers survived long enough to return images and measurements before succumbing to the heat and pressure. Those images revealed a landscape of flat, rocky plains under an orange-tinted sky, with slabs of basalt stretching in every direction. The atmospheric density at the surface was so great that sunlight filtering through the clouds created a diffuse, dim illumination, like a deeply overcast day on Earth, but bathed in amber. Radar mapping, most comprehensively performed by NASA's Magellan spacecraft in the early 1990s, revealed a surface dominated by volcanic plains covering roughly 80% of the planet. Venus has more volcanoes than any other planet in the solar system, with over 1,600 major volcanic features identified. Some of these are enormous shield volcanoes. Mont Mons, the tallest, rises approximately 8 kilometers above the surrounding terrain. There are also pancake domes, unusual flat-topped volcanic structures not found on Earth, formed by the eruption of highly viscous lava under Venus's extreme atmospheric pressure. Whether Venus is still volcanically active has been debated for decades. Recent analyses of data from the European Space Agency's Venus Express orbiter detected transient increases in sulfur dioxide in the upper atmosphere, which could indicate ongoing volcanic eruptions. Even more compelling, a study published in 2023 re-examined Magellan radar images taken months apart and identified a volcanic vent that appeared to change shape between observations, suggesting active lava flow during the Magellan mission itself. If confirmed by future missions, this would make Venus one of only a few bodies in the solar system with confirmed present-day bulb. Venus also rotates in the opposite direction from most planets, a phenomenon called retrograde rotation. A single Venusian day, measured from sunrise to sunrise, lasts about 117 Earth days. Its rotation is so slow that a day on Venus is actually longer than a year on Venus, since it completes one orbit around the Sun in about 225 Earth days. Why Venus rotates backwards and so slowly is not fully understood. One possibility is that a massive collision early in the planet's history reversed its spin. Another suggests that tidal interactions between the thick atmosphere and the solid body gradually slowed and eventually reversed the rotation over billions of years. As we pull away from Venus, its brilliant white cloud tops reflect sunlight so efficiently that it becomes the brightest natural object in Earth's sky after the sun and moon. It hangs in the evening or morning sky like a lantern, beautiful and serene from the outside, concealing one of the most extreme environments in the solar system beneath its calm exterior. Ahead of us now, the next world is familiar. It is home. Earth appears gradually as we continue outward from Venus. At first, it is simply another bright point of light among the stars. But as the distance closes, something becomes immediately different. Color. Earth is saturated with it. Deep blue oceans cover more than 70% of the surface. White cloud systems spiral across entire hemispheres. Continents show muted greens and browns. Ice caps gleam at both poles. After the grey desolation of Mercury and the featureless white clouds of Venus, Earth is startling in its complexity. It is, as far as we currently know, the only world in the solar system where liquid water exists openly on the surface, where weather systems cycle through familiar patterns of evaporation and precipitation, and where life has taken hold with such thoroughness that it has reshaped the planet's atmosphere, oceans, and even its geology. Earth orbits the Sun at an average distance of approximately 150 million kilometers, a distance so useful as a measuring unit that astronomers named it the astronomical unit. One orbit takes 365.25 days. The planet rotates once every 24 hours, tilted on its axis by about 23.4 degrees relative to its orbital plane, and that tilt is responsible for the seasons. When the northern hemisphere tilts toward the sun, it receives more direct sunlight and experiences summer. 6 months later, the southern hemisphere takes its turn. This cycle has repeated for billions of years and has shaped the behavior of every living organism that has ever existed on the planet's surface. Earth's atmosphere is roughly 78% nitrogen and 21% oxygen, with the remaining fraction composed of argon, carbon dioxide, water vapor, and trace gases. That oxygen is not a geological product, it is biological. Photosynthetic organisms, first cyanobacteria billions of years ago, and later plants, have pumped oxygen into the atmosphere continuously, transforming it from a reducing environment rich in carbon dioxide and methane into the breathable mixture we depend on today. The presence of free oxygen in a planetary atmosphere is so unusual, so thermodynamically unstable, without constant biological replenishment, that it is considered one of the most promising biosignatures astronomers search for when examining the atmospheres of distant exoplanets. Beneath the atmosphere, Earth's interior remains remarkably active. The planet possesses a layered structure, a thin silicate crust, a thick mantle of slowly convecting rock, a liquid outer core of iron and nickel, and a solid inner core at the very center, where pressures exceed 3 million atmospheres. The liquid outer core generates Earth's magnetic field through a self-sustaining dynamo, and that magnetic field extends far into space, creating a magnetosphere that deflects the solar wind and protects the atmosphere from being gradually stripped away. Without that magnetic shield, Earth might have suffered a fate more similar to Mars, which lost most of its atmosphere over billions of years after its own magnetic field faded. Earth's crust is divided into tectonic plates that move slowly across the surface, driven by convective currents in the underlying mantle. Where plates collide, mountains rise and subduction zones pull crustal material back into the interior. Where plates diverge, new crust forms along mid-ocean ridges. This process, plate tectonics, is unique among the rocky planets. Mercury, Venus, and Mars show no evidence of active plate tectonics today. Earth's tectonic activity recycles carbon, regulates atmospheric composition over geological timescales, builds continents, and creates the volcanic activity that has continuously reshaped the planet's surface for billions of years. It is one of several interconnected systems, along with the magnetic field, the water cycle, and biological activity, that together maintain the conditions necessary for life as we understand it. From space, none of this complexity is immediately obvious. What strikes the eye is the thin blue line of atmosphere curving along the planet's edge, the slow swirl of cloud formations, and the sheer amount of water. Earth is a water world. Its oceans contain 1.335 billion cubic kilometers of water, filling basins that reach depths of more than 10 kilometers in places like the Mariana Trench. These oceans moderate the planet's temperature, store and release enormous quantities of heat, drive weather patterns, and host ecosystems ranging from sunlit coral reefs to the absolute darkness of abyssal plains where life persists under crushing pressure, sustained by chemical energy rather than sunlight. One companion travels with Earth. The Moon orbits at an average distance of about 384,400 kilometers, close enough to be the most prominent object in Earth's night sky. It is large relative to its parent planet, roughly 1/4 of Earth's diameter, making the Earth-Moon system more like a double planet than a typical planet-satellite pair. The leading theory for the Moon's formation involves a Mars-sized body colliding with the young Earth approximately 4.5 billion years ago, blasting an enormous amount of debris into orbit, which gradually coalesced into the Moon. This giant impact hypothesis explains several observed features. The Moon's relatively small iron core, its depletion in volatile elements, and its remarkably similar oxygen isotope ratios compared to Earth's mantle. The Moon's surface tells two stories. The bright, heavily cratered highlands are ancient, dating back more than 4 billion years, preserving a record of the intense bombardment that characterized the early solar system. The dark, smoother Maria are vast plains of solidified basaltic lava that flooded large impact basins between roughly 3.9 and 3.1 billion years ago, after which volcanic activity on the Moon essentially ceased. Today the Moon is geologically quiet. It has no atmosphere, no magnetic field, and no plate tectonics. Its surface is exposed directly to the solar wind, micrometeorites, and cosmic radiation. Yet it remains scientifically invaluable, preserving a geological record that Earth's active surface has long since erased. We leave Earth and its Moon behind now and continue outward. The space between Earth's orbit and the next planet is noticeably wider. Mars orbits the Sun at an average distance of about 228 million kilometers, roughly 1.5 astronomical units. It takes 687 Earth days to complete a single orbit. As we approach, the planet's distinctive color becomes apparent even from a great distance. A dusty, reddish-brown surface that earned it the name of an ancient god of war. Mars is a small world, just 6,779 kilometers in diameter, roughly half the size of Earth. Its mass is only about 1/10 of Earth's. Its atmosphere is thin, composed almost entirely of carbon dioxide, with surface pressures averaging just 0.6% of Earth's sea level pressure. Standing on the surface of Mars, you would find a sky tinted butterscotch or pinkish during the day, colored by fine iron oxide dust suspended in the thin air. Temperatures vary dramatically, from a relatively mild -20 degrees Celsius near the equator on a summer afternoon to -125 degrees Celsius at the winter poles. Mars is a cold, dry, windswept desert. But it was not always this way. One of the most significant discoveries of the past several decades of Mars exploration is that liquid water once flowed across the Martian surface. Evidence for this exists everywhere. Ancient river channels carved into the landscape meander across the southern highlands. Layered sedimentary deposits suggest long-lived lakes. The enormous Valles Marineris Canyon system, stretching more than 4,000 kilometers across the planet's equatorial region, shows signs of water erosion in addition to tectonic fracturing, and orbital spectrometers have identified clay minerals and sulfate deposits that can only form in the presence of liquid water over extended periods. Mars, during its first billion years or so, may have been warm enough and wet enough to sustain rivers, lakes, and possibly even a shallow ocean covering much of the northern lowlands. What changed is still debated, but the loss of the planet's global magnetic field appears central. Without a magnetic shield, the solar wind began stripping away the Martian atmosphere molecule by molecule. As atmospheric pressure dropped, liquid water became increasingly unstable on the surface. Over hundreds of millions of years, Mars dried out. Water retreated underground, froze into polar ice caps, and became locked in subsurface permafrost. Today, water ice exists at both Martian poles, mixed with frozen carbon dioxide in seasonal caps that grow and shrink with the Martian seasons. Subsurface ice deposits have been confirmed at mid-latitudes by orbital radar and by the Phoenix lander, which directly observed water ice just centimeters beneath the surface near the North Pole in 2008. Mars also holds the solar system's most extreme topography. Olympus Mons, a shield volcano in the Tharsis region, rises approximately 21.9 kilometers above the surrounding plains, making it the tallest known mountain on any planet. Its base spans roughly 600 kilometers, an area comparable to the state of Arizona. Olympus Mons and its neighboring Tharsis volcanoes grew so large because Mars lacks plate tectonics. On Earth, A volcanic hotspot produces a chain of progressively smaller volcanoes as the plate moves over it. On Mars, the crust remains stationary, allowing a single volcano to accumulate lava over billions of years until it reaches extraordinary dimensions. Vas Marineris, the Great Canyon system, is equally dramatic, stretching more than 4,000 kilometers in length, reaching depths of up to 7 kilometers, and spanning as much as 200 kilometers wide in places. It dwarfs Earth's Grand Canyon in every dimension. It likely began as a network of tectonic fractures associated with the uplift of the Tharsis Bulge, and was subsequently widened by erosion, landslides, and possibly catastrophic flooding. Mars has 2 small moons, Phobos and Deimos, both irregularly shaped and heavily cratered. Phobos, the larger of the two at roughly 22 kilometers across, orbits so close to Mars that it completes one orbit every 7 hours and 39 minutes, faster than Mars rotates. This means Phobos rises in the west and sets in the east when viewed from the Martian surface. Tidal forces are gradually pulling Phobos closer, and within the next 50 million years or so it will either collide with Mars or, more likely, be torn apart by tidal stresses and form a temporary ring around the planet. Deimos, smaller and more distant, orbits much more slowly and is gradually spiraling outward. As we leave Mars behind, the inner solar system ends. We have passed through the realm of the rocky planets. 4 worlds huddled relatively close to the Sun, each with a solid surface, each shaped by heat from within and bombardment from without. Mercury, Venus, Earth, Mars. They are as different from one another as 4 siblings could be. One is a cratered remnant with an oversized core. One is a pressure cooker wrapped in acid clouds. One is a living world of water and air. And one is a frozen desert that remembers an ancient ocean it can no longer hold. Ahead lies a broader, emptier space. Between the orbit of Mars and the orbit of the next great world, Jupiter, a vast region stretches across hundreds of millions of kilometers. This region is not entirely empty. It is populated by millions of rocky and metallic fragments left over from the earliest days of the solar system, remnants of a world that was never allowed to form. We are approaching the asteroid belt. The asteroid belt is not what most people imagine. Popular culture has embedded an image of dense, dangerous fields of tumbling rock, spacecraft weaving between boulders at every turn. The reality is profoundly different. The asteroid belt is mostly empty space. If you were to stand on any single asteroid and look around, the nearest neighboring asteroid would almost certainly be invisible to the naked eye, lost somewhere beyond the horizon of darkness, hundreds of thousands or even millions of kilometers away. Spacecraft that have passed through the belt, including Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, Cassini, New Horizons, and Juno, did so without any special maneuvering to avoid collisions. The distance between objects are simply too vast for accidental encounters, and yet the belt contains millions of objects. Current estimates suggest there may be between 1 and 2 million asteroids larger than 1 kilometer in diameter, and hundreds of millions of smaller bodies down to the size of pebbles and dust grains. Their combined mass, however, is startlingly small. If every asteroid in the belt were gathered together into a single body, the result would be an object less than half the diameter of Earth's moon, with a total mass roughly 4% of the moon's. The belt is not a failed planet in the dramatic sense. It is a region where a planet was prevented from forming, and the difference matters. The reason lies with Jupiter. During the early solar system, as the planets were still assembling from the protoplanetary disk of gas and dust surrounding the young sun, Jupiter formed quickly and grew massive. Its gravitational influence stirred the orbits of the rocky debris in the region between Mars and its own orbit, increasing collision velocities to the point where impacts between objects were more likely to shatter them apart than to build them together. Instead of gently accreting into a single planet, the material in this zone was ground down, scattered, and depleted. Much of the original mass was ejected entirely, flung out of the belt by gravitational interactions with Jupiter over hundreds of millions of years. What remains today is a remnant population, a thin scattering of survivors from a process that consumed most of the original material. The asteroids that survive are scientifically extraordinary. They are among the oldest objects in the solar system, preserved fragments from the very earliest stages of planetary formation, roughly 4.6 billion years ago. Some have remained virtually unchanged since that time. Carbonaceous chondrite asteroids, found primarily in the outer belt, contain organic molecules, water-bearing minerals, and pre-solar grains that formed before the solar system itself existed. These objects are time capsules. Studying them reveals the composition of the original solar nebula and the chemical processes that ultimately led to the formation of planets, and, on at least one of those planets, life. The largest object in the asteroid belt is Ceres, a dwarf planet, roughly 940 kilometers in diameter. Ceres is large enough for its own gravity to have pulled it into a roughly spherical shape, distinguishing it from the irregular forms of smaller asteroids. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018 and revealed a world far more complex than expected. Ceres possesses a thin but detectable exosphere. Its surface is dark, composed of a mixture of clays, carbonates, and salts. Most strikingly, Dawn discovered bright deposits of sodium carbonate in several craters, most prominently in Orcator crater, where brilliant white spots stood out against the otherwise dark terrain. These deposits appear to have been brought to the surface by cryovolcanic activity, briny water rising from a subsurface reservoir and depositing salts as the water sublimated away in the vacuum. The implication is remarkable. Ceres, a small body in the asteroid belt, may harbor or have recently harbored liquid water beneath its surface. Vesta, the second largest asteroid at roughly 525 kilometers across, is a very different kind of object. Dawn also visited Vesta, orbiting it from 2011 to 2012. Vesta is a differentiated body, meaning it was once hot enough internally for its materials to separate by density, forming an iron core, a rocky mantle, and a basaltic crust. In this sense, Vesta is more like a miniature planet than a simple rock. Its southern hemisphere is dominated by an enormous impact basin called Rhea Silvia, approximately 505 kilometers wide, with a central peak rising about 22 kilometers from the basin floor, one of the tallest known mountains in the solar system. The impact that created Rhea Silvia was so violent that it excavated material from deep within Vesta's interior and launched fragments into space. Many of those fragments eventually found their way to Earth as a class of meteorites called howardites, eucrits, and diogenites, making Vesta one of the few solar system bodies whose surface material we can study directly in laboratories without a dedicated sample return mission. Beyond the main belt, two groups of asteroids share Jupiter's orbit. These are the Trojan asteroids, clustered around the two stable Lagrange points 60 degrees ahead of and behind Jupiter, in its path around the Sun. The Trojans are believed to number in the hundreds of thousands for objects larger than 1 kilometer, and may rival the main belt in total population. Their composition appears darker and more primitive than many main belt asteroids, suggesting they may have originated in the outer solar system and been captured into their current orbits during a period of planetary migration early in the solar system's history. NASA's Lucy mission, launched in 2021, is currently on a 12-year journey to visit multiple Trojan asteroids, the first dedicated mission to explore this population. We leave the asteroid belt behind now. Ahead, the distances between worlds grow dramatically. The space between the asteroid belt and Jupiter spans hundreds of millions of kilometers of emptiness. But as we cross that void, the next world announces itself long before we arrive. Not through visibility alone, but through influence. Jupiter's gravity shapes the motion of everything around it. It perturbs the orbits of asteroids. It captures comets. It has gathered a family of moons so large and numerous that it resembles a miniature solar system. Jupiter is not merely the largest planet, it is the dominant gravitational architect of the outer solar system. Jupiter orbits the Sun at an average distance of approximately 778 million kilometers, more than 5 times the Earth-Sun distance. It completes one orbit every 1186 Earth years. As we approach, the planet's sheer size becomes overwhelming. Jupiter is 139,820 kilometers in diameter, more than 11 times the width of Earth. Its volume could contain more than 1,300 Earths. Its mass is approximately 318 times that of Earth. And in fact, Jupiter contains more mass than all other planets in the solar system combined. It is composed primarily of hydrogen and helium, with no solid surface in the conventional sense. What we see when we look at Jupiter is the top of an atmosphere that extends downward for thousands of kilometers, gradually transitioning from gas to liquid to an exotic state of matter found nowhere on Earth. The atmosphere itself is one of the most visually striking features in the solar system. Alternating bands of light zones and dark belts wrap around the planet parallel to its equator, driven by powerful jet streams that reach speeds of several hundred kilometers per hour. These bands are composed of ammonia ice crystals, ammonium hydrosulfide, and water, arranged in complex layers. The light zones are regions of rising air, where ammonia ice forms bright, high-altitude clouds. The dark belts are regions of sinking air, where deeper, darker cloud layers become visible. The boundaries between zones and belts are turbulent, producing enormous storm systems, wave patterns, and vortices that can persist for years or even centuries. The most famous of these storms is the Great Red Spot, an anticyclonic storm larger than Earth that has been observed continuously since at least the 19th century and may have existed for much longer. The Great Red Spot rotates counterclockwise with wind speeds at its edges exceeding 400 kilometers per hour. Its distinctive red color is not fully understood, though it is thought to result from complex photochemical reactions involving sulfur, phosphororganic compounds in the upper atmosphere exposed to ultraviolet radiation. In recent decades, the Great Red Spot has been observed to be slowly shrinking, its longitudinal extent decreasing from roughly 40,000 kilometers in the late 1800s to approximately 16,000 kilometers today. Whether it will eventually dissipate entirely or stabilize at a smaller size remains an open question. Beneath the visible cloud tops, Jupiter's atmosphere deepens into increasingly dense layers. At depths where pressure reaches roughly 10 times Earth's sea level pressure, temperatures rise above the boiling point of water. Deeper still, the hydrogen gas is compressed so heavily that it transitions into a liquid. And at depths corresponding to pressures of roughly 2 million atmospheres, liquid hydrogen undergoes a phase transition into metallic hydrogen, a state of matter in which hydrogen atoms are packed so closely that their electrons move freely between atoms, conducting electricity like a metal. This layer of metallic hydrogen is believed to extend for tens of thousands of kilometers and is responsible for generating Jupiter's extraordinarily powerful magnetic field, the strongest of any planet in the solar system. Jupiter's magnetosphere extends millions of kilometers into space, enveloping its moons and creating intense radiation belts that would be lethal to unprotected spacecraft and certainly to any biological organism. At the very center of Jupiter, a core likely exists, though its nature remains uncertain. Earlier models proposed a distinct rocky or icy core, roughly 10 to 20 times the mass of Earth, surrounded by the metallic hydrogen envelope. More recent data from NASA's Juno mission, which has been orbiting Jupiter since 2016, suggests the core may be dilute, a fuzzy region where heavy elements are mixed gradually into the surrounding hydrogen rather than concentrated in a sharp boundary. This finding has implications for how Jupiter formed and how giant planets develop in general. Jupiter's system of moons is vast. As of current counts, Jupiter has over 90 known moons, ranging from tiny irregular captures just a few kilometers across to the 4 Galilean moons, each of which is a world in its own right. These 4, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in 1610 and were among the first objects observed orbiting another body, providing early evidence that not everything in the cosmos revolved around the Earth. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Tidal forces from Jupiter and resonant gravitational interactions with Europa and Ganymede continuously flex Io's interior, generating enormous amounts of heat. Hundreds of active volcanoes dot its surface, some producing lava fountains that reach hundreds of kilometers above the surface. The constant volcanic resurfacing means Io has virtually no impact craters, its entire surface being replaced on geological timescales measured in thousands of years rather than billions. Europa, the next moon outward, is almost the opposite in surface appearance. Its exterior is a smooth shell of water ice, crisscrossed by a network of reddish-brown fractures and ridges. Beneath that ice shell, strong evidence indicates the presence of a global liquid water ocean, kept warm by tidal heating similar to but less intense than what drives Io's volcanism. Europa's ocean may contain more liquid water than all of Earth's oceans combined. The combination of liquid water, energy from tidal heating, and the potential for chemical nutrients from the rocky seafloor makes Europa one of the most promising candidates for extraterrestrial life in the solar system. NASA's Europa Clipper mission, launched in 2024, is designed to perform detailed flybys of Europa, studying the ice shell, the ocean beneath, and the moon's potential habitability. Ganymede, the largest moon in the solar system at 268 kilometers in diameter, is larger than the planet Mercury. It possesses its own magnetic field, the only moon known to do so. Like Europa, Ganymede is believed to harbor a subsurface ocean sandwiched between layers of ice deep within its interior. Its surface displays 2 distinct terrain types: ancient, dark, heavily cratered regions, and younger, lighter, grooved terrain formed by tectonic processes. Callisto, the outermost Galilean moon, is one of the most heavily cratered bodies in the solar system. Its surface is ancient and geologically dead, a frozen record of the intense bombardment period of the early solar system. Yet even Callisto may possess a thin subsurface ocean, inferred from magnetic field measurements made by the Galileo spacecraft. Jupiter and its moons form a system of extraordinary scientific richness, but our journey does not end here. We continue outward, deeper into the outer solar system, where the distances grow even greater and the sunlight grows weaker. Ahead lies a world of elegant beauty, a planet defined by the most spectacular ring system in the solar system. Saturn announces itself differently from Jupiter. There is no overwhelming sense of gravitational dominance, no crushing radiation belts reaching out to greet approaching spacecraft. Instead, there is light. As we cross the vast emptiness between Jupiter and Saturn, a distance of more than 600 million kilometers, the first sign of the next world is a faint but unmistakable glow. Sunlight reflecting not from the planet alone, but from an enormous system of rings that encircle it. Even from hundreds of millions of kilometers away, those rings catch the light and send it back toward us, marking Saturn's position in the outer solar system. Like a beacon of geometry and ice, Saturn orbits the Sun at an average distance of approximately 1.43 billion kilometers, nearly 10 times the Earth-Sun distance. A single orbit takes 29.5 Earth years. The planet itself is the second largest in the solar system, with an equatorial diameter of roughly 120,536 kilometers, wide enough to contain more than 9 Earths lined up side by side. Yet despite its size, Saturn is remarkably light. Its average density is only about 0.687 grams per cubic centimeter, less than that of water. This famous fact, often cited as meaning Saturn would float if placed in a sufficiently large ocean, reflects the planet's composition. Like Jupiter, Saturn is composed primarily of hydrogen and helium, with no solid surface in the conventional sense. Its visible exterior is the top of an atmosphere that deepens for thousands of kilometers, transitioning gradually through layers of increasing pressure and temperature until hydrogen becomes liquid and, deeper still, likely transitions into a metallic state similar to Jupiter's interior, though under somewhat less extreme conditions. Saturn's atmosphere is visually subtler than Jupiter's. The same basic pattern of alternating bands exists, driven by powerful jet streams, but the colors are more muted, washed out by a thicker haze of ammonia crystals in the upper atmosphere that gives the planet an overall golden or pale yellow appearance. Beneath that haze, Saturn's weather is anything but calm. Wind speeds near the equator can exceed 1,800 kilometers per hour, among the fastest measured on any planet. Periodic storms erupt from deeper atmospheric layers, sometimes growing large enough to encircle the planet entirely. These great white spots, as they are known, appear roughly once every Saturnian year and can persist for months before dissipating. The most recent, observed in 2010 and 2011 by the Cassini spacecraft, began as a small, bright disturbance in the northern hemisphere and expanded within weeks into a storm system that wrapped around the entire planet, generating enormous amounts of lightning and disrupting the atmospheric banding for years afterward. Deep within Saturn, the internal structure likely mirrors Jupiter's in broad terms, but with important differences. Saturn's core is believed to be somewhat smaller and less distinct, possibly extending diffusely into the surrounding layers. The planet generates more heat than it receives from the Sun, a phenomenon it shares with Jupiter. One mechanism proposed to explain this excess heat involves helium rain. As Saturn's interior has cooled over billions of years, helium in the upper metallic hydrogen layer may have become immiscible, forming droplets that rain downward through the lighter hydrogen, releasing gravitational potential energy as heat. This process, if occurring, would also explain the observed depletion of helium in Saturn's outer atmosphere compared to solar composition. Saturn's magnetic field, while strong by terrestrial standards, is weaker than Jupiter's and nearly perfectly aligned with the planet's rotation axis, a configuration that remains difficult to explain under standard dynamo theory and continues to puzzle planetary scientists. But it is Saturn's rings that have captivated human attention since Galileo first observed them through his telescope in 1610, though he could not resolve them clearly enough to understand what he was seeing. Later observations by Christian Huygens in 1655 correctly identified the rings as a flat disk surrounding the planet. From Earth, the rings appear solid and monolithic, but they are composed of countless individual particles, ranging in size from tiny grains of dust to boulders several meters across, with a small number of objects reaching tens of meters. The vast majority of ring material is water ice, often mixed with small amounts of rocky impurities that tint some ring regions with subtle shades of brown or grey. The ring system is extraordinarily wide, but astonishingly thin. The rings extend from roughly 7,000 kilometers above Saturn's cloud tops to approximately 80,000 kilometers outward. spanning a total width of more than 70,000 kilometers. Yet the vertical thickness of the main rings is typically only about 10 meters, and in some regions as little as a few meters. If the rings were scaled down to the diameter of a typical football field, they would be thinner than a sheet of paper. This extreme flatness is a natural consequence of particle collisions within the ring plane. Any particle on an inclined orbit repeatedly collides with other particles, losing energy with each collision until its orbit is circularized and flattened into the plane of the rings. Over time, the entire system settles into a remarkably thin disk. The rings are divided into several major regions, designated by letters in the order of their discovery. The brightest and most prominent are the A and B rings, separated by the Cassini division, a gap roughly 4,800 kilometers wide that is visible from Earth through a modest telescope. The Cassini division is not truly empty, but contains much less material than the adjacent rings, and the particles within it are darker and more sparse. The C ring, closer to the planet than the B ring, is fainter and more translucent. Beyond the A ring, the narrow F ring is a dynamic, constantly changing structure shepherded by two small moons, Prometheus and Pandora, whose gravitational interactions create braids, kinks, and clumps in the ring material. Farther out still, the G and E rings are extremely tenuous, the E ring being fed primarily by cryovolcanic plumes erupting from the moon Enceladus. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our understanding of the ring system. Cassini revealed that the rings are far more dynamic and complex than previously imagined. Density waves and bending waves ripple through the rings in response to gravitational tugs from Saturn's moons, creating patterns that can be used to measure the mass and mechanical properties of the ring material. Propeller-shaped disturbances mark the locations of small moonlets embedded within the rings, objects too small to clear complete gaps but large enough to push ring particles aside locally. Cassini also discovered that the rings interact with Saturn's atmosphere, with ring material raining down onto the planet along magnetic field lines in a process sometimes called ring rain. One of the most surprising findings from Cassini's final orbits, during which the spacecraft dove repeatedly through the gap between Saturn and its innermost ring, was evidence suggesting the main rings may be relatively young. Measurements of the total mass of the B ring indicated it was lighter than expected, and the relative brightness of the ring ice, not yet darkened significantly by meteoritic contamination, suggested an age of perhaps 100 million to a few hundred million years, far younger than Saturn itself. If the rings are indeed young, they may have formed from the breakup of a large moon or comet that ventured too close to Saturn and was torn apart by tidal forces. This remains an active area of research, and the age of the rings is one of the most debated questions in planetary science today. Saturn's system of moons is second only to Jupiter's in number and far exceeds it in diversity. More than 140 moons are currently known, ranging from tiny irregular captures just a few kilometers across to Titan, the second largest moon in the solar system and one of the most remarkable worlds ever explored. Titan orbits Saturn at a distance of approximately 1.2 million kilometers. With a diameter of 5,150 kilometers, it is larger than the planet Mercury. But what makes Titan truly extraordinary is its atmosphere. Titan is the only moon in the solar system with a dense, substantial atmosphere, a thick envelope of nitrogen with a surface pressure roughly 5 times that of Earth's sea level atmosphere. This atmosphere extends hundreds of kilometers above the surface and is laced with complex organic chemistry. Methane in the upper atmosphere is broken apart by solar ultraviolet radiation and energetic particles from Saturn's magnetosphere, initiating chains of chemical reactions that produce increasingly complex hydrocarbons, and nitriles. These compounds form a thick orange haze that completely obscures the surface in visible light, giving Titan its distinctive featureless amber appearance when viewed from outside. Beneath that haze, Titan possesses a landscape unlike anything else in the solar system. The European Space Agency's Huygens probe, which descended through Titan's atmosphere and landed on the surface in January 2005, revealed a world of dark, rounded pebbles composed of water ice scattered across a flat plain of darker material. Drainage channels carved into the landscape indicated that liquid had recently flowed across the surface. But on Titan, with surface temperatures of roughly -179 degrees Celsius, the liquid is not water. It is methane and ethane. Titan has a complete hydrological cycle, analogous to Earth's water cycle, but operating with hydrocarbons. Methane evaporates from surface reservoirs, rises into the atmosphere, forms clouds, and falls as rain, carving channels and filling lakes and seas before evaporating again. Cassini's radar instruments, capable of seeing through Titan's opaque haze, mapped the surface and discovered large bodies of liquid, concentrated primarily in the northern polar region. Kraken Ma, the largest, covers an area of roughly 400,000 square kilometers, comparable in size to the Caspian Sea on Earth. Ligeia Mare and Pung Mare are smaller but still substantial. These are the only known stable bodies of liquid on any surface other than Earth's. Their composition is predominantly methane and ethane, and radar measurements suggest depths of at least several hundred meters in some areas. Titan's southern hemisphere also contains lake basins, most of which appeared dry during the Cassini mission, suggesting seasonal variation. A full Titan year lasts roughly 29 Earth years, so seasonal changes unfold on timescales that challenge human observation. Titan's surface geology includes vast equatorial dune fields, composed not of silicate sand, but of organic particles that have settled out of the atmosphere over millions of years. These dunes stretch for hundreds of kilometers, shaped by winds that blow predominantly eastward near the equator. Mountain ridges of water ice rise above the surrounding terrain in some regions. Cryovolcanic features may also exist, though their identification from orbital data remains debated. Beneath the icy crust, gravitational measurements from Cassini suggest the presence of a global subsurface ocean of liquid water, likely mixed with ammonia and salts. This places Titan alongside Europa and Enceladus in the small but growing list of solar system bodies that may harbor liquid water beneath their surfaces. Enceladus, by contrast, is tiny. With a diameter of only about 504 kilometers, it could fit comfortably within the borders of a mid-sized European country. Before Cassini arrived at Saturn, Enceladus was known to have an unusually bright, reflective surface, but it was not expected to be geologically active. What Cassini discovered changed planetary science permanently. Near the south pole of Enceladus, a region of fractured young terrain is crisscrossed by 4 prominent fissures informally called tiger stripes. From these fissures, enormous plumes of water vapor, ice crystals, and organic molecules erupt continuously into space, reaching heights of hundreds of kilometers above the surface. Cassini flew directly through these plumes multiple times, analyzing their composition with onboard instruments. The plumes contain water, salts, silica, nanoparticles, molecular hydrogen, and a variety of organic compounds, including complex macromolecular organics. The silica nanoparticles are particularly significant because they form only in hot water interacting with rock, suggesting that hydrothermal vents exist on the floor of Enceladus's subsurface ocean, similar to the deep-sea hydrothermal vents on Earth that support thriving ecosystems in complete darkness. The gravitational data and the plume composition together paint a picture of a small moon with a global liquid water ocean beneath an ice shell roughly 20 to 25 kilometers thick at the South Pole, thinning to perhaps 5 kilometers in the fractured region where the plumes emerge. Tidal heating from gravitational interactions with Saturn and the orbital resonance with the Moon, Dione, provides the energy that keeps this ocean liquid. Enceladus, despite being small enough to fit within a single terrestrial country, possesses all three ingredients generally considered necessary for life as we know it: liquid water, chemical energy, and organic molecules. It is arguably the most accessible ocean world in the solar system because its ocean material is being continuously delivered into space, available for future spacecraft to sample without ever needing to drill through an ice shell. The material ejected from Enceladus does not simply vanish. Much of it falls back to the surface, coating Enceladus in fresh, bright ice and giving it the highest albedo of any body in the solar system. But a significant fraction escapes the Moon's weak gravity and enters orbit around Saturn, forming the vast diffuse E-ring. This ring extends from roughly the orbit of Mimas to well beyond the orbit of Titan, and its existence is maintained almost entirely by the ongoing eruptions on Enceladus. Saturn's other moons contribute to the system's richness. Mimas, small and heavily cratered, bears the enormous Herschel crater, an impact scar so large relative to the Moon's size that the impact nearly shattered it. Iapetus displays one of the most striking surface features in the solar system: a two-toned coloration with one hemisphere as dark as coal and the other as bright as fresh snow, likely caused by the accumulation of dark material swept up from retrograde outer moons, combined with thermal feedback effects. Hyperion is an irregularly shaped body with a bizarre sponge-like surface of deep, sharp-edged craters. Phoebe, a small, dark retrograde moon, is likely a captured Kuiper Belt object, a refugee from the outer solar system now trapped in Saturn's gravitational embrace. We leave Saturn behind, and as we do, the rings narrow to a thin, bright line, then fade entirely as distance swallows the detail. The Sun, which near Saturn already appears roughly 100 times dimmer than it does from Earth, continues to shrink behind us. The outer solar system grows darker, colder, and emptier. The distance between the worlds we have visited so far has been increasing steadily, but ahead of us, the gaps widen further still. The next two planets, Uranus and Neptune, orbit at distances so great that they were unknown to ancient astronomers, invisible to the naked eye, discovered only through the patient work of telescopes and mathematics. They are the ice giants, fundamentally different from Jupiter and Saturn in composition and behavior, and they are among the least explored worlds in the solar system. Uranus was the first planet discovered with a telescope. Every world we have visited so far, Mercury, Venus, Mars, Jupiter, and Saturn, was known to ancient civilizations, visible to the unaided eye, and tracked across the night sky for thousands of years, before anyone understood what they truly were. Uranus broke that pattern. On the night of March 13, 1781, the astronomer William Herschel, observing from his garden in Bath, England, noticed an object through his homemade reflecting telescope that did not behave like a star. It moved. Over subsequent nights and weeks, its motion became clear, and after careful observations and calculations by Herschel and others, the object was confirmed as a new planet, the first addition to the solar system in recorded human history. The discovery doubled the known size of the planetary system overnight. Uranus orbits the Sun at an average distance of approximately 2.87 billion kilometers, roughly 19 times the Earth-Sun distance. A single orbit takes 84 Earth years. At this distance, sunlight is roughly 400 times weaker than at Earth. Uranus receives so little solar energy that it appears cold, pale, and visually subdued, a world of muted blue-green wrapped in featureless haze when viewed from afar. The planet's blue-green color results from methane in its upper atmosphere. Methane absorbs red wavelengths of sunlight efficiently, while allowing blue and green wavelengths to scatter back toward an observer, tinting the planet with that distinctive aquamarine hue. Beneath the methane layer, the atmosphere is composed primarily of hydrogen and helium, similar in broad composition to Jupiter and Saturn, but fundamentally different in structure. Uranus and Neptune are classified as ice giants rather than gas giants because a substantial fraction of their mass consists of heavier volatile compounds, water, ammonia, and methane, compressed into a dense, hot fluid layer that makes up most of the planet's interior. This distinguishes them sharply from Jupiter and Saturn, which are dominated by hydrogen and helium throughout. The internal structure of Uranus is believed to consist of a small rocky core, perhaps 1 to 2 times the mass of Earth, surrounded by a thick mantle of water, ammonia, and methane compressed under extreme pressures. At these depths, temperatures reach thousands of degrees Celsius, despite the frigid exterior, and the volatile compounds exist in an exotic state, neither truly liquid nor truly gas by everyday standards. Some theoretical models suggest that conditions deep within Uranus and Neptune may be extreme enough to dissociate methane molecules, liberating carbon atoms that could be compressed into diamond. The idea of diamond rain falling through the interiors of ice giants remains speculative, but is supported by laboratory experiments that have successfully produced nanoscale diamonds under comparable pressures and temperatures. The most striking physical characteristic of Uranus is its axial tilt. The planet rotates on its side, with an axial tilt of approximately 98 degrees, while most planets spin roughly upright relative to their orbital planes. Uranus rolls along its orbit like a ball. This extreme tilt means that during parts of its 84-year orbit, one pole points almost directly at the Sun, while the other faces deep space. Each pole experiences roughly 42 years of continuous sunlight, followed by 42 years of darkness. The cause of this extraordinary tilt is generally attributed to one or more giant impacts during the early solar system, collisions so powerful that they knocked the planet onto its side. The details remain unclear, and some models suggest that gravitational interactions with other bodies during planetary migration could have contributed. The extreme tilt produces unusual seasonal effects. When Voyager 2 flew past Uranus in January 1986, the planet's southern pole was pointed almost directly at the Sun, and the visible atmosphere appeared remarkably bland, with very few cloud features detected. For years, Uranus was considered the least interesting of the giant planets atmospherically, but later observations from the Hubble Space Telescope and ground-based observatories equipped with adaptive optics revealed that as Uranus approached its equinox in 2007, when sunlight fell equally on both hemispheres, atmospheric activity increased significantly. Bright cloud features, storm systems, and banded structures emerged, demonstrating that Uranus possesses genuine weather driven by seasonal changes, though on timescales that dwarf anything experienced on Earth. Uranus has a magnetic field, but it is deeply unusual. On most planets with magnetic fields, the field is roughly aligned with the rotation axis and centered near the planet's core. On Uranus, the magnetic field is tilted approximately 59 degrees from the rotation axis and offset from the planet's center by roughly 1/3 of the planet's radius. This produces a magnetic field that wobbles dramatically as the planet rotates, creating a magnetosphere that is asymmetric and chaotic by the standards of other planets. The origin of this unusual field geometry is not fully understood, but may relate to the composition and convective properties of the interior fluid layers. Uranus possesses a ring system, though far more modest than Saturn's. The rings were discovered in 1977 when astronomers observed a series of brief dips in starlight as Uranus passed in front of a distant star, indicating narrow, dark rings encircling the planet. Voyager 2 confirmed and imaged these rings, revealing at least 13 distinct narrow rings composed of very dark particles, with albedos among the lowest of any known ring material in the solar system. The rings are thought to be relatively young and may be continually replenished by the breakup of small moons or collisions among ring particles. 27 known moons orbit Uranus, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were imaged by Voyager 2 during its flyby. Miranda, the smallest and innermost of the 5, displayed one of the most bizarre surfaces ever photographed. Despite being only about 470 kilometers in diameter, Miranda's surface is a chaotic patchwork of different terrain types. Enormous rectangular or trapezoidal features called coronae dominate portions of the surface bounded by networks of ridges and grooves. Verona Rupes, a cliff face on Miranda, drops approximately 20 kilometers from top to bottom, making it one of the tallest known cliffs in the solar system. How such a small moon came to possess such a tortured surface remains debated. One hypothesis involves tidal heating driven by an ancient orbital resonance with other moons that has since been broken. Another suggests that Miranda was shattered by a large impact and reassembled gravitationally with the different terrain types, reflecting incompletely mixed-done fragments. Voyager 2 remains the only spacecraft to have visited Uranus. Its flyby in January 1986 lasted only a few hours of close approach, during which it gathered most of the data we possess about the planet, its rings, and its moons. Since then, no dedicated mission has returned. Uranus remains one of the least explored planets in the solar system, a world known primarily through a single brief encounter and decades of distant telescopic observation. We continue outward. The distance between Uranus and the next planet is greater still. More than 6 billion kilometers of nearly empty space separate the two ice giants. The Sun, already faint at Uranus, diminishes further. At Neptune's distance, it would appear as little more than a very bright star, providing roughly 900 times less light than it does at Earth. The outer solar system is a realm of cold and darkness on a scale that is difficult to internalize. And yet, at the far edge of the planetary system, one final giant world orbits in that darkness, and it proved to be far more dynamic and surprising than anyone expected. Neptune was the first planet discovered through mathematics rather than direct observation. By the early 19th century, astronomers had noticed that Uranus was not following its predicted orbit precisely. Small but persistent deviations suggested that the gravitational pull of an unknown body was perturbing its motion. In the 1840s, the mathematicians Urbain Le Verrier in France and John Couch Adams in England independently calculated where such a body should be located. On September 23, 1846, the astronomer Johann Galle at the Berlin Observatory pointed his telescope to the position predicted by Le Verrier and found Neptune within 1 degree of the calculated location, a triumph of celestial mechanics and one of the most elegant demonstrations of Newtonian gravity in the history of science. Neptune orbits the Sun at an average distance of approximately 4.5 billion kilometers, about 30 astronomical units. One orbit takes roughly 165 Earth years. Neptune has completed only a single orbit since its discovery. The planet is slightly smaller than Uranus in diameter, at approximately 49,528 kilometers, but notably more massive, roughly 17 times the mass of Earth compared to Uranus's 14.5. This higher density suggests a somewhat different internal composition or structure, with a larger proportion of heavier materials. Despite receiving even less solar energy than Uranus, Neptune's atmosphere is far more active. When Voyager 2 arrived at Neptune in August 1989, after a 12-year journey through the outer solar system, it found a world of vivid blue with dramatic atmospheric features. The most prominent was the Great Dark Spot, an anticyclonic storm system roughly the size of Earth, accompanied by bright white clouds of methane ice crystals at high altitude. Smaller storm systems and cloud bands were also visible. Wind speeds near the Great Dark Spot were measured at approximately 2,100 kilometers per hour, the fastest winds recorded on any planet in the solar system. The intensity of Neptune's atmospheric activity is puzzling because the planet receives so little energy from the Sun. The answer lies within. Neptune radiates roughly 6 times more energy than it receives from sunlight, indicating a substantial internal heat source. This internal energy drives convection and atmospheric circulation far more vigorously than solar heating alone could explain. The mechanism generating this internal heat is not entirely understood. Slow gravitational contraction, residual heat from formation, and possibly differentiation processes within the interior have all been proposed. Whatever the source, it produces a level of atmospheric dynamism that was entirely unexpected for a planet so far from the Sun, and made Neptune one of the great surprises of the Voyager mission. Neptune's magnetic field, like that of Uranus, is highly tilted and offset from the planet's center. The field axis is inclined approximately 47 degrees from the rotation axis and displaced from the center by roughly half the planet's radius. This produces a similarly complex, wobbling magnetosphere. The fact that both ice giants share this unusual magnetic field geometry suggests it may be a fundamental characteristic related to their interior structure, perhaps originating in a conductive fluid shell at intermediate depth, rather than deep within a metallic hydrogen core as in Jupiter and Saturn. Neptune also possesses rings, though they are faint and narrow. Before Voyager 2's arrival, ground-based observations had detected arcs, partial rings, that appeared to exist only along portions of an orbit. Voyager 2 revealed that the arcs are in fact the densest concentrations within complete but very tenuous rings. The outermost ring, known as the Adams ring, contains several of these arc structures where ring material is clumped together rather than distributed uniformly. The gravitational influence of the small moon Galatea is thought to help confine material in these arcs, though the precise mechanism remains a subject of study. Neptune's largest moon is Triton, and it is one of the most scientifically compelling objects in the outer solar system. Triton is large, approximately 2,707 kilometers in diameter, and it orbits Neptune in a retrograde direction, opposite to the planet's rotation. No other large moon in the solar system has a retrograde orbit. This strongly suggests that Triton did not form alongside Neptune, but was instead captured, most likely from the Kuiper Belt, the vast ring of icy objects that lies just beyond Neptune's orbit. The capture process would have been violent, involving significant tidal heating, as Triton's initially elliptical orbit was gradually circularized by gravitational interaction with Neptune. That tidal heating may have kept Triton's interior warm enough to maintain geological activity for an extended period, perhaps even sustaining a subsurface ocean. Voyager 2's flyby of Triton revealed a young, sparsely cratered surface with a remarkable variety of terrain types. Much of the surface is covered by nitrogen and methane ices, giving it one of the highest albedos in the solar system. The southern hemisphere displayed a strange terrain, sometimes described as cantaloupe terrain, due to its resemblance to the skin of a cantaloupe melon, composed of roughly circular dimples covering vast areas. Most dramatically, Voyager 2 observed active geysers on Triton's surface, plumes of nitrogen gas and dark particulates rising approximately 8 kilometers above the surface, before being carried horizontally by thin upper atmosphere winds, leaving dark streaks across the icy plains. These were among the first confirmed active eruptions observed on any body in the outer solar system, and they demonstrated that even at the frigid edge of the planetary system, geological activity persists. With Neptune, the planetary solar system ends. There are no more giant worlds beyond this point, no more thick atmospheres, no more vast storm systems, no more ring systems catching the faint sunlight. Beyond Neptune, the solar system changes character entirely. The worlds become smaller, colder, darker, and far more widely scattered. The distances between them grow immense, and the story shifts from one of grand planetary machinery to one of ancient frozen remnants drifting in silence at the edge of everything the sun can still claim as its own. Beyond Neptune, the solar system does not end, it transforms. The realm of the giant planets gives way to something older, colder, and far more dispersed. There are no more massive worlds with thick atmospheres and powerful magnetic fields. No more ring systems catching sunlight. No more moons with active volcanoes or subsurface oceans warmed by tidal forces. What lies ahead is a vast, frozen archive stretching across billions of kilometers, populated by countless small icy bodies that have drifted in near total darkness since the solar system was young. This is the Kuiper Belt, and it is one of the most important regions in the solar system for understanding how everything began. The Kuiper Belt extends from roughly the orbit of Neptune, at about 30 astronomical units from the Sun, outward to approximately 50 astronomical units. In raw distance, that means it spans a region from about 4.5 billion kilometers to roughly 7.5 billion kilometers from the Sun. Within that enormous volume, an estimated tens of thousands of objects larger than 100 kilometers in diameter orbit slowly through the dark, along with millions of smaller bodies. These are not asteroids in the conventional sense. They are composed primarily of frozen volatiles, water ice, methane ice, ammonia ice, and nitrogen ice, mixed with darker organic compounds and rocky material. They are remnants of the outer protoplanetary disk, the raw building materials from which the giant planets formed, left over because no planet grew large enough in this region to sweep them up. The existence of the Kuiper Belt was predicted long before it was observed. In 1951, the Dutch-American astronomer Gerard Kuiper suggested that a belt of small icy bodies might exist beyond Neptune, though his specific reasoning was somewhat different from the modern understanding. Other astronomers, including Kenneth Edgeworth in 1943 and Fred Whipple in earlier work on comets, had also speculated about reservoirs of frozen material in the outer solar system. The region is sometimes called the Edgeworth-Kuiper Belt, in recognition of these multiple contributors, but the belt remained theoretical until 1992, when astronomers David Jewett and Jane Liu, after years of patient searching, discovered a faint object designated 1992 QB1 orbiting beyond Neptune. This was the first confirmed Kuiper Belt object, other than Pluto, and it opened the floodgates. Within a few years, dozens more objects were found. Within 2 decades, more than 1,000 had been catalogued, and the true nature of the outer solar system began to come into focus. The Kuiper Belt is not a uniform ring. Its population is divided into several dynamical classes based on orbital characteristics. The classical Kuiper Belt objects, sometimes informally called Q1Os, after the prototype 1992 QB1, occupy relatively circular, stable orbits between roughly 42 and 48 astronomical units. These objects are thought to have formed approximately where they now orbit, relatively undisturbed since the early solar system. Their orbits are gently inclined and mildly eccentric, and they represent the most pristine population in the belt. Some classical objects travel in pairs, binary systems, where 2 bodies of similar size orbit a common center of mass, suggesting they form together through gentle gravitational collapse rather than violent collision. A second major population consists of the resonant objects, bodies whose orbital periods are locked into specific mathematical ratios with Neptune's orbital period. The most famous of these are the Plutinos, objects trapped in a 3-2 orbital resonance with Neptune, meaning they complete exactly 2 orbits for every 3 orbits Neptune completes. Pluto itself is the largest and best-known Plutino. This resonance is not coincidental. It is a consequence of Neptune's outward migration early in the solar system's history. As Neptune moved outward from its formation location, its gravitational influence swept through the outer disk, capturing objects into resonant orbits, like a snowplow pushing debris into organized piles. The existence of large resonant populations is one of the strongest pieces of evidence for the planetary migration models that have reshaped our understanding of solar system formation. Pluto occupies a unique position in both the Kuiper Belt and in the cultural history of astronomy. Discovered by Clyde Tombaugh in 1930 after a systematic photographic search at Lowell Observatory in Arizona, Pluto was classified as the 9th planet for 76 years. It was always an oddity among the planets, tiny, distant, with a highly elliptical and inclined orbit that sometimes brought it closer to the Sun than Neptune. Its true nature became clearer only as the Kuiper Belt itself was discovered and characterized. Pluto, it turned out, was not a misfit planet. It was the largest known member of an enormous population of icy bodies beyond Neptune. In 2006, the International Astronomical Union formally reclassified Pluto as a dwarf planet, a decision that remains controversial among some scientists and much of the public, but reflects a deeper understanding of the solar system's architecture. Whatever its classification, Pluto is a remarkable world. NASA's New Horizons spacecraft flew past Pluto on July 14, 2015, after a 9.5-year journey from Earth, and what it revealed transformed a blurry point of light into a complex, geologically active world. Pluto is approximately 2,377 kilometers in diameter, smaller than Earth's moon, with a surface composed of nitrogen ice, methane ice, and carbon monoxide ice overlying a substrate of water ice. The most striking feature revealed by New Horizons was Sputnik Planitia, an enormous heart-shaped basin, roughly 1,000 kilometers across, filled with a vast plain of nitrogen ice. This plain is not ancient. Its surface is remarkably smooth, virtually free of impact craters, indicating it has been geologically resurfaced within the last few million years at most. Convective cells visible within the nitrogen ice suggest a slow churning process where warmer nitrogen rises from below, spreads across the surface, cools and sinks again at the cell boundaries, constantly renewing the terrain. Beyond Sputnik Planitia, New Horizons revealed mountains of water ice rising several core kilometers above the surrounding terrain. Their summits dark, with organic material called tholins, complex reddish-brown compounds formed by the irradiation of simple molecules like methane and nitrogen. Pluto's surface displayed an extraordinary range of terrains: cratered highlands, smooth plains, jumbled, blocky regions, and areas of bladed terrain where tall fins of methane ice have been sculpted by sublimation into formations resembling the penitentes found at high altitudes on Earth. The variety was astonishing for a world so small and so cold. Pluto possesses a thin but genuine atmosphere, composed primarily of nitrogen with traces of methane and carbon monoxide. This atmosphere is sustained by the sublimation of surface ices, and its pressure varies as Pluto moves along its eccentric orbit, increasing when closer to the Sun and decreasing when farther away. New Horizons, the atmosphere backlit by the Sun during departure, revealing multiple haze layers extending more than 200 kilometers above the surface, composed of tiny particles of tholin produced by photochemical reactions in the upper atmosphere. The sight of those haze layers, glowing blue against the blackness of space, was among the most beautiful images ever returned from the outer solar system. Pluto's largest moon, Charon, is so large relative to Pluto that the two are sometimes considered a binary system. Charon is approximately 1,212 kilometers in diameter, roughly half the size of Pluto. The two bodies orbit a common center of mass located in the space between them, and they are tidally locked, each always showing the same face to the other. Charon's surface, imaged in detail by New Horizons, is dominated by water ice and displays its own geological complexity. A vast canyon system stretches across much of the moon's equatorial region, and the northern pole is covered by a dark reddish cap, informally named Mordor Macula, likely composed of tholins that originated from Pluto's escaping atmospheric gases, captured and processed by ultraviolet radiation on Charon's cold surface. 4 smaller moons, Nix, Hydra, Kerberos, and Styx, orbit the Pluto-Charon system at greater distances, all small and irregularly shaped, likely formed from the debris of the same giant impact that created Charon. After its encounter with Pluto, New Horizons continued deeper into the Kuiper Belt. On January 1, 2019, it flew past a small Kuiper Belt object named Arrokoth, formerly known as 2014 MU69. Arrokoth is a contact binary, 2 roughly spherical lobes joined together at a narrow neck, giving it the appearance of a flattened snowman. It is approximately 36 kilometers in its longest dimension. Its surface is uniformly reddish, coated in tholins, and remarkably smooth, with very few impact craters. The gentle contact between its 2 lobes suggests it formed through a slow, low-velocity merger of 2 smaller bodies, rather than a violent collision, providing direct evidence for the gentle accretion processes that built larger bodies in the early solar system. Arrokoth is the most distant and most primitive object ever visited by a spacecraft, a frozen relic from the very beginning of planetary formation. The Kuiper Belt contains several other dwarf planets in addition to Pluto. Eris, discovered in 2005, is slightly smaller than Pluto in diameter, but slightly more massive, with a highly inclined and eccentric orbit that carries it far beyond the classical Kuiper Belt. Its surface appears bright and icy, covered in frozen nitrogen and methane. Eris possesses a small moon named Dysnomia. The discovery of Eris was one of the key events that prompted the reclassification of Pluto, since the existence of a body similar in size raised the question of whether Eris should also be called a planet, or whether both belong to a different category entirely. Makemake, discovered in 2005, is another large Kuiper Belt dwarf planet, roughly 2/3 the diameter of Pluto, with a surface rich in frozen methane and ethane. Haumea, also discovered around the same time, is notable for its extreme elongation, shaped more like an egg than a sphere, likely the result of a rapid rotation period of just under 4 hours. Haumea also possesses a ring, discovered in 2017, making it one of only a few small bodies known to have rings. 2 small moons, Hyakka and Namaka, orbit Haumea, probably fragments from an ancient Calypso that also produced a family of smaller objects, sharing similar orbits and surface compositions. Beyond the classical Kuiper Belt, the scattered disk extends the population of icy bodies to much greater distances. Scattered disk objects have highly elliptical orbits that can carry them from near Neptune's orbit out to hundreds of astronomical units from the Sun. These orbits were produced by close gravitational encounters with Neptune that flung the objects onto elongated paths. The scattered disk is thought to be the primary source of short-period comets, objects that occasionally have their orbits perturbed inward by gravitational interactions, sending them diving toward the inner solar system, where solar heating sublimates their ices and produces the glowing tails visible from Earth. One of the most intriguing scattered disk objects is Sedna, discovered in 2003. Sedna's orbit is extraordinary. Its closest approach to the Sun is approximately 76 astronomical units, well beyond the influence of Neptune, and its farthest point extends to roughly 900 astronomical units, with an orbital period of approximately 11,000 years. Sedna's orbit cannot be explained by gravitational interactions with any known planet. Something else must have shaped it, perhaps a passing star in the Sun's birth cluster, perhaps an as-yet undiscovered planet in the far outer solar system, perhaps the gravitational influence of the galactic tide. Sedna exists in a region between the Kuiper Belt and the hypothetical Oort cloud, a transitional zone that challenges simple models of solar system structure. As we drift beyond the scattered disk, the population of known objects thins dramatically. The Sun, already reduced to a bright point of light, grows fainter still. At 100 astronomical units from the Sun, sunlight is 10 thousand times weaker than at Earth. Temperatures hover just a few tens of degrees above absolute zero. The solar system here feels less like a neighborhood and more like a memory, the gravitational echo of a star whose warmth can no longer be felt. But the Sun's influence has not yet ended. Far ahead, beyond the last known Kuiper Belt objects, beyond even Sedna's distant orbit, two boundaries remain. The first is the heliopause, where the solar wind finally surrenders to the pressure of interstellar space. The second is the theoretical outer edge of the Oort cloud, the true gravitational frontier of the solar system. Both lie ahead, and both represent something remarkable, the places where our stars reach after extending across billions upon billions of kilometers finally comes to an end. The solar system has one more boundary to cross before the journey truly ends, and it is not defined by rock, ice, or gravity alone. It is defined by wind. The solar wind, that continuous stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, has been with us since the beginning of this journey. Near the Sun, it is dense and fast. At Earth's orbit, it is still strong enough to shape the magnetosphere and push cometary tails away from the Sun. At Jupiter, it remains measurable. At Neptune, it has weakened considerably, but still flows outward, things carrying with it the Sun's magnetic field, extending the Sun's influence far beyond the last planet. But the solar wind is not infinite. It is pushing against something. Beyond the solar system, the interstellar medium, a thin but vast sea of gas, dust, and cosmic rays that fills the space between stars, exerts its own pressure. Somewhere far beyond Neptune, far beyond the Kuiper Belt, the outward push of the solar wind and the inward pressure of the interstellar medium reach equilibrium. The wind slows, heats, compresses, and finally stops. That boundary is the edge of the heliosphere, and crossing it means leaving the Sun's domain entirely. The heliosphere is not a simple sphere with a clean edge. It is a dynamic, evolving structure shaped by the Sun's motion through the galaxy and by variations in the solar wind itself. The Sun and its entire system of planets, moons, asteroids, and comets are moving through the local interstellar medium at roughly 23 kilometers per second. This motion compresses the heliosphere on the leading side and stretches it on the trailing side, creating an asymmetric shape, sometimes compared to the wake of a boat moving through water, though the precise geometry of the heliosphere's tail remains debated. Some models suggest a long comet-like tail extending for hundreds of astronomical units. Others propose a more rounded shape, with the trailing edge not dramatically different in distance from the leading edge. The true shape is not yet known with certainty because we have only 2 data points from spacecraft that have crossed the boundary, both crossed on roughly the same side. Those 2 spacecraft are Voyager 1 and Voyager 2, and their journeys to the edge of the heliosphere and beyond represent one of the most extraordinary achievements in the history of human exploration. Voyager 1 and Voyager 2 were launched in 1977, within weeks of each other, on trajectories designed to take advantage of a rare alignment of the outer planets that occurs roughly once every 175 years. This alignment allowed each spacecraft to use gravitational assists from one planet to accelerate toward the next, visiting multiple worlds on a single trajectory. Voyager 2 launched first on August 20, 1977, followed by Voyager 1 on September 5. Despite launching second, Voyager 1 was placed on a faster trajectory and reached Jupiter and Saturn before its twin. Both spacecraft completed their primary missions spectacularly, returning the first detailed images and measurements of Jupiter, Saturn, and their moons. Voyager 2 continued onward to Uranus and Neptune, becoming the only spacecraft to visit either world, while Voyager 1's trajectory after Saturn was angled northward, out of the ecliptic plane, sacrificing further planetary encounters for a faster path toward interstellar space. After their planetary encounters were complete, both Voyagers continued outward, still functioning, still transmitting, powered by radioisotope thermoelectric generators that convert the heat from decaying plutonium-238 into electricity. These generators produce less power each year as the plutonium decays, and by the time the Voyagers approached the heliosphere boundary, they were operating on a fraction of their original power, with most scientific instruments shut down to conserve energy. But the instruments most critical for detecting the heliosphere boundary, the plasma science instruments, the magnetic field sensors, and the cosmic ray detectors, remained active. The journey from the outer planets to the heliosphere boundary took decades. The boundary lies far beyond the Kuiper Belt, at distances that dwarf even the vast spaces between the outer planets. As the Voyagers moved outward, the solar wind around them grew progressively weaker. The density of charged particles dropped. The magnetic field carried by the wind became more tenuous, and simultaneously, the flux of galactic cosmic rays, high-energy particles, originating from sources outside the solar system, began to increase, no longer fully deflected by the heliosphere's protective bubble. The first major structural boundary the Voyagers encountered was the termination shock, the region where the solar wind abruptly slows from supersonic to subsonic speed as it begins to feel the counterpressure of the interstellar medium. This is not the edge of the heliosphere itself, but rather the beginning of the end. Voyager 1 crossed the termination shock in December 2004 at a distance of approximately 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at roughly 84 astronomical units on the opposite side of the heliosphere. The difference in distance confirmed that the heliosphere is not symmetrical, compressed on one side by the interstellar medium's pressure and the Sun's galactic motion. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind piles up, heats, and becomes compressed against the interstellar medium. The heliosheath is a chaotic place. The solar wind, no longer flowing smoothly outward, becomes turbulent and unpredictable. The magnetic field fluctuates. The plasma environment changes character. Both Voyagers spent years crossing this region, transmitting data about conditions that no instrument had ever measured before. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, on August 25, 2012, at a distance of approximately 121.6 astronomical units from the Sun. The crossing was identified by a dramatic and sudden change in the particle environment. The density of solar wind particles dropped to near zero. The flux of galactic cosmic rays, which had been gradually increasing, jumped sharply to levels consistent with the full, unshielded interstellar medium. The magnetic field direction changed, shifting from the orientation carried by the solar wind to a different orientation, consistent with the local interstellar magnetic field. Voyager 1 had left the heliosphere. It had entered interstellar space. Voyager 2 followed on November 5, 2018, crossing the heliopause at approximately 119 astronomical units. Its crossing was in some ways even more scientifically valuable than Voyager 1's, because Voyager 2's plasma science instrument was still fully operational, allowing direct measurement of the plasma density, temperature, and velocity on both sides of the boundary. The data confirmed that the heliopause is a relatively sharp boundary, with the transition from solar wind plasma to interstellar plasma occurring over a distance of less than 1 astronomical unit. On the interstellar side, the plasma was denser, cooler, and flowing in a different direction, consistent with the local interstellar medium through which the Sun moves. Both Voyagers are now in interstellar space, the first human-made objects to reach this environment. As of now, Voyager 1 is more than 160 astronomical units from the Sun, roughly 24 billion kilometers away. Voyager 2 is somewhat closer, at approximately 135 astronomical units. Radio signals from the Voyagers, traveling at the speed of light, take more than 22 hours to reach Earth. Commands sent from NASA's Deep Space Network take equally long to arrive. Every communication is a conversation with a delay measured in nearly a full Earth day. The Voyagers will not last forever. Their power output decreases by roughly 4 watts per year. Scientific instruments have been shut down progressively as available power has declined. By the mid-2030s, there may not be enough power remaining to operate any instruments at all. The transmitters will eventually fall silent. The Voyagers will become inert, drifting through interstellar space on trajectories that will carry them past other stars, only after tens of thousands of years. Voyager 1 will pass within roughly 6 light-years of the star, Gliese 445, in approximately 40,000 years. Voyager 2 will pass near the star, Ross 248, in roughly the same time frame. Neither spacecraft will come particularly close to these stars. They will simply drift, silent and dark, carrying with them golden records engraved with images, sounds, and greetings from Earth. Messages in a bottle, cast into an ocean, so vast that the probability of their recovery is almost zero, but whose existence says something important about the species that sent them. The heliopause, however, is not the final edge of the solar system. It is the edge of the Sun's atmospheric influence, the boundary where its wind can no longer hold back the interstellar medium, but gravitationally, the Sun's reach extends far beyond. Objects bound by the Sun's gravity exist at distances hundreds and even thousands of times greater than the heliopause. The Voyagers have left the heliosphere, but they have not left the gravitational domain of the Sun. They are still falling through a region where the Sun, though reduced to a bright point of light indistinguishable from any other star, to a casual observer, still exerts enough gravitational pull to hold objects in orbit. And it is in this vast, gravitationally bound but wind-free region that the final structure of the solar system is believed to exist. The Oort cloud, a theoretical shell of dormant comets surrounding the Sun at distances so great that it bridges the gap between our star and the nearest others. The Oort cloud has never been directly observed. No telescope has resolved its individual members. No spacecraft has come close to reaching it. It exists as a prediction built from indirect evidence and theoretical necessity, a structure inferred from the behavior of comets that occasionally fall inward from immense distances, arriving on orbits so elongated that they must originate from a reservoir far beyond anything we have yet explored. The Oort cloud, if it exists as models predict, represents the true outer boundary of the solar system, and it is there, in the deepest cold and the most absolute silence, that our journey finally ends. The Oort cloud has never been seen. No telescope has imaged its members. No spacecraft has approached it. No radar has pinged its contents. No instrument of any kind has directly confirmed its existence. It remains even now a theoretical structure inferred entirely from indirect evidence and the demands of gravitational logic. and yet it may be the largest structure associated with our Sun, a spherical shell of dormant comets, enclosing everything we have visited on this journey, extending outward to distances so extreme that the solar system begins to overlap with the gravitational influence of neighboring stars. The concept was proposed in 1950 by the Dutch astronomer Jan Oort, who studied the orbits of long-period comets, those that arrive in the inner solar system on trajectory so elongated that their orbital periods are measured in thousands or even millions of years. These comets do not come from the Kuiper Belt. Their orbits are too long, too inclined, and too randomly oriented. They arrive from every direction, not confined to the plane of the ecliptic like the planets and most Kuiper Belt objects. Oort concluded that these comets must originate from a vast, roughly spherical reservoir surrounding the Sun at enormous distances, a cloud of frozen objects so far away that even gentle gravitational perturbations from passing stars, the galactic tide, or encounters with giant molecular clouds could dislodge them from their stable orbits and send them falling inward toward the Sun. The Oort cloud is believed to begin at roughly 2005, zeros and astronomical units from the Sun, and extend outward to perhaps 100,000 or even 200,000 astronomical units. At its outer boundary, the Sun's gravitational influence becomes so weak that objects can be pulled free entirely by the gravity of other stars. To grasp the scale of this structure, consider that the heliopause, which the Voyager spacecraft spent 35 years reaching, lies at roughly 120 astronomical units. The inner edge of the Oort cloud is at least 15 to 40 times farther than that. Its outer edge is nearly 1,000 times farther still. If the Voyagers continue at their current speeds, they will not reach the inner Oort cloud for another 300 years. They will not exit the outer boundary for roughly 30,000 years. The Oort cloud is so vast that light itself takes more than a year to cross it. The population of the Oort cloud is estimated to contain trillions of objects, most of them small, icy bodies, a few kilometers across or less. Their combined mass is uncertain, but may total several Earth masses. These objects are believed to have formed much closer to the Sun, in the region between the giant planets during the earliest epochs of the solar system. As Jupiter, Saturn, Uranus, and Neptune migrated through the young protoplanetary disk, their gravitational interactions scattered vast quantities of icy debris outward. Some of this material was ejected from the solar system entirely. Some was placed into extremely distant, but still gravitationally bound orbits, settling over billions of years into the roughly spherical distribution we now call the Oort cloud. The cloud's spherical shape, rather than a flat disk like the Kuiper Belt, is a consequence of the randomizing effect of external gravitational perturbations over time. Passing stars and the tidal force of the Milky Way itself gradually randomize the orbital inclinations of Oort cloud objects, spreading them into a shell surrounding the Sun in every direction. The objects within the Oort cloud exist in a state of extraordinary isolation. Each one drifts through darkness so complete that the Sun from there would appear as merely one bright star among many. Surface temperatures hover just a few degrees above absolute zero. There is no solar wind at these distances, no heliosphere, no magnetic field from the Sun to interact with. The environment is indistinguishable from interstellar space in almost every measurable sense, except for one crucial fact: these objects are still gravitationally bound to our star. They orbit the Sun, albeit on timescales so long that their motion would be imperceptible across an entire human lifetime. A single orbit at the outer edge of the Oort cloud might take tens of millions of years. Occasionally, something disturbs this silence. A passing star drifts close enough to the Sun's neighborhood to gravitationally perturb a handful of Oort cloud objects. The slow tidal pull of the Milky Way shifts orbits incrementally over millions of years. A close encounter with another star, perhaps once every several 100,000 years, sends a shower of objects cascading inward. Most of these perturbed objects drift harmlessly through the outer solar system, invisible and undetected. But some, those nudged onto orbits that carry them into the inner solar system, begin a long fall toward the sun that can take hundreds of thousands of years. As they approach the warmth, frozen volatiles sublimate, producing the glowing commas and tails that characterize comets visible from Earth. These long-period comets are messengers from the Oort cloud, the only direct evidence we have of its existence. When a previously unknown comet appears in Earth's sky, on a trajectory suggesting an orbital period of millions of years, it has likely traveled from the Oort cloud, carrying material that has been frozen in nearly pristine condition since the solar system formed 4.6 billion years ago. The outer boundary of the Oort cloud is the true gravitational edge of the solar system. Beyond it, objects are no longer bound to the sun. They belong to the galaxy itself, drifting through interstellar space under the collective gravitational influence of billions of stars, rather than the singular pull of one. This boundary is not a wall or a line. It is a gradual fading, a region where the sun's gravitational claim weakens to the point where it can no longer hold material against the competing tug of the broader galaxy. The transition is gentle, imperceptible, and vastly extended across space. There is no moment of crossing, no sudden change. The solar system simply dissolves, its influence thinning to nothing across a region so large that the concept of boundaries becomes almost meaningless. And yet here, at the outermost reaches of everything our sun can claim, the journey we began close to the solar surface comes to its natural end. We have traveled from a place of blinding light and overwhelming heat, where hydrogen fuses into helium at 15 million degrees, to a place of absolute cold and perfect stillness, where ice drifts unchanged for billions of years, and the sun is just another star. We have passed through the inner solar system, where 4 small rocky worlds endure conditions, ranging from the cratered desolation of Mercury to the living oceans of Earth. We crossed the asteroid belt, a corridor of ancient debris that marks the boundary between the terrestrial and giant planets. We visited the gas giants, Jupiter and Saturn, worlds so massive that they contain most of the solar system's planetary matter, surrounded by moons, complex enough to be worlds in their own right. We continued through the ice giants, Uranus and Neptune, underexplored and enigmatic, with interiors that may rain diamonds and magnetic fields that defy simple explanation. Beyond the planets, we drifted through the Kuiper Belt, a frozen archive of the solar system's earliest materials, home to Pluto and thousands of other icy remnants. We followed the Voyage spacecraft to the heliopause, where the solar wind finally surrenders to the interstellar medium. And now, at the Oort cloud, we have reached the place where the sun's gravity itself fades to nothing. The distances we have covered are real, but they resist intuition. From the sun to Mercury is 58 million kilometers. From the sun to the outer Oort cloud is perhaps 15 trillion kilometers or more. The entire journey spans a factor of roughly 250,000 in distance. If the sun were placed at one end of a football field and Mercury were positioned 1 centimeter from it, the outer Oort cloud would lie more than 2 kilometers away. The solar system is not a compact neighborhood of planets. It is a structure of almost incomprehensible scale, with the familiar planets occupying only the tiniest fraction of its true extent and the vast majority of its volume filled with cold, dark, empty space. Nothing about this vastness is hostile. It simply is. The silence of the outer solar system is not the silence of absence, but the silence of patience. Objects here have orbited without interruption for longer than complex life has existed on Earth. Ice that formed alongside the sun has never been warmed, never been altered, never been touched. The Oort cloud is a library of the solar system's infancy, preserved in cold storage at the edge of everything, waiting for no one. The sun from here is indistinguishable from the other stars. It glows steadily among them, unremarkable in brightness, unremarkable in color. An observer at this distance would have no reason to suspect that this particular star hosts a system of planets. That one of those planets carries liquid water. That on that planet's surface, living beings have looked upward and wondered about the nature of the universe. The solar system, seen from its own edge, is invisible. Its grandeur, its complexity, its 4.5 billion years of geological and biological history, all of it compressed into a point of light, no different from any other. And beyond this edge, beyond the last gravitationally bound fragment of ice, the interstellar medium stretches onward in every direction. The nearest neighboring star, Proxima Centauri, lies roughly 4.24 light-years away, a distance of approximately 268,000 astronomical units. Even the outer Oort cloud, vast as it is, reaches only partway toward this nearest stellar neighbor. The spaces between stars are larger still than the spaces within a stellar system. The Milky Way galaxy, which contains the Sun, along with hundreds of billions of other stars, stretches roughly 100,000 light-years across. And beyond the Milky Way, billions of other galaxies populate an observable universe approximately 93 billion light-years in diameter. The journey we have taken from the Sun to the edge of its gravitational influence is among the longest continuous voyages that can be made within a single stellar system. And yet in the context of the galaxy, it barely registers. In the context of the observable universe, it vanishes entirely. This is not a diminishment, it is a perspective. The solar system is one structure among trillions, built from the same physics, the same elements, the same processes that shape every other star and its surrounding material. Its uniqueness, if it has any, lies not in its scale, but in what happened on one small, warm, wet world orbiting at just the right distance from an ordinary star. The journey is over now. The Sun is far behind. The planets are memories of light and gravity encountered along the way. The Kuiper Belt has faded. The heliosphere has closed behind us. The Oort cloud thins to nothing. Ahead, there is only starlight, faint and patient, stretching in every direction without end. The solar system, everything it contains, everything it has produced, everything it has witnessed across nearly 5 billion years, rests quietly behind us, a single ember glowing in an ocean of night, and in that night, everything else begins.